Moving on. Consider potentiometers in the following circuits. In the first circuit, consider a series combination of a 560 ohm resistor and a potentiometer adjusted such that 70% of 1 kΩ, or 700 ohms, appears between terminals B and C. In the second circuit, consider a parallel combination of an 820 ohm resistor and a potentiometer also adjusted such that 70% of 1 kΩ, or 700 ohms, appears between terminals B and C. See if you can determine the total resistance seen by the source for these circuits incorporating potentiometers at these various settings. Also, for each of these types of circuits, series or parallel, consider the consequences of adjusting the potentiometer to the upper and lower extremes. In this case, an upper limit of 1 kΩ and a lower limit of 0 ohms. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following values. The series combination of a 560 and a 700 ohm resistor is 1,260, or more appropriately, roughly 1.3 kiloohms. Let's now consider the upper and lower extremes for the series configuration. When the potentiometer is adjusted such that 100% of 1 kiloohm appears in series with the 560 ohm resistor, the series circuit presents a resistance of 1,560 ohms, or more appropriately, roughly 1.6 kiloohms. This is the upper limit of resistance achievable for this particular circuit. Conversely, when the potentiometer is adjusted such that 0% of 1 kiloohm appears in series with a 560 ohm resistor, the series circuit presents a resistance of 560 ohms. This is the lower limit of resistance achievable for this particular circuit. Even with the potentiometer essentially out of the picture, the 560 ohm resistor in series never lets total resistance drop below 560 ohms. This series combination essentially acts as a failsafe to keep at least some level of resistance inside a circuit, thereby ensuring current remains controlled and manageable. Let's now take a look at potentiometers in parallel configurations. The parallel combination of an 820 and a 700 ohm resistor is roughly 377.6 ohms. Let's now consider the upper and lower extremes. When the potentiometer is adjusted such that 100% of 1 kiloohm appears in parallel with the 820 ohm resistor, the parallel circuit presents a total resistance of roughly 450.5 ohms. This is the upper limit of resistance achievable for this particular circuit. Conversely, when the potentiometer is adjusted such that 0% of 1 kiloohm appears in parallel with the 820 ohm resistor, the entire parallel circuit is essentially shorted out such that the source sees no resistance. Recall that shorted elements, i.e. 0 ohm paths in parallel circuits, short out the entire circuit such that it presents a minimal opposition to current, i.e. 0 ohms of resistance. All current will be routed around the circuit through the 0 ohm short. Before we bring this lecture to a close, let's check out a couple real-world potentiometers. Here's an example of an inexpensive 1 kilo ohm potentiometer meant for low-power applications and features a small adjustment screw on top. You'll note there is no label clearly identifying the A, B, or C terminals. Not a big deal. We can use an ohm meter to figure out which terminal is which. When I check the resistance between the two outside terminals, the ohm meter registers a constant 1064 ohms, regardless of how vigorously I turn the screw. These are obviously the fixed terminals A and C, and this potentiometer most likely has a nameplate value of 1 kiloohms. Let's call the top terminal A and the bottom terminal C. If I transfer one lead of the ohm meter to the central B terminal, the ohm meter demonstrates there is 626.6 ohms of resistance between B and C. If I check the resistance between A and B, the ohm meter demonstrates the remaining 444.3 ohms of resistance appears between A and B. With the ohm meter positioned in this manner, a couple turns in the adjustment screw changes the resistance between A and B to 380.6 ohms. When I switch the ohm meter back to B and C, the ohm meter demonstrates the remaining 691 ohms of resistance appears between B and C. It makes sense. For every ohm decrease on one side represents a corresponding increase on the other side, and vice versa. Here's another example of a potentiometer obviously intended for high-power applications. Rather than use an adjustment screw, this device uses a sliding wiper on a track that clearly illustrates the internal functionality of a potentiometer. When I check the resistance between the two outside screw terminals, the ohm meter registers a constant 106.2 ohms regardless of how hard, far, or fast I drag the wiper along the track. These are obviously the fixed terminals A and C. Let's call the left terminal A and the right terminal C. If I transfer one lead of the ohm meter to the upper B terminal, the ohm meter demonstrates there is roughly 63.7 ohms of resistance between B and C. If I check resistance between A and B, the ohm meter demonstrates the remaining 41.8 ohms of resistance appears between A and B. With the ohmmeter positioned in this manner, the gentle slide along the rail changed the resistance of A to B to roughly 78.2 ohms. When I switch the ohmmeter back to B and C terminals, the ohmmeter demonstrates the remaining 27 ohms of resistance appears between B and C. Again, for every ohm increase on one side, it represents a corresponding decrease on the other, and vice versa. Finally, here's yet another example of a potentiometer. Rather than using an adjustment screw or a sliding wiper, this device uses a turning knob. When I check the resistance between the two outer terminals, the ohmmeter registers a constant 5 kiloohms regardless of how viciously I twist the knob. These are obviously the fixed terminals A and C, and this potentiometer most likely has a nameplate value of 5 kiloohms. Let's call the top terminal A and the bottom terminal C. If I transfer one lead of the ohmmeter to the central B terminal, the ohmmeter demonstrates there is roughly 2.8 kiloohms of resistance between B and C. If I check resistance between A and B, the ohmmeter demonstrates the remaining 2.1 kiloohms of resistance appears between A and B. With the ohmmeter positioned in this manner, a turn on the knob changes the resistance between A and B to roughly 1 kiloohm. When I switch the ohmmeter back to the B and C terminals, the ohmmeter demonstrates the remaining 4 kiloohms of resistance appears between B and C. Again, for every ohm decrease on one side represents a corresponding increase in the other, and vice versa. Before bringing this lecture to a close, allow me to make a comment about taper, which is the relationship of resistance to position. There are two types of common tapers, one known as linear and the other known as logarithmic taper. For the purposes of this introductory lecture, we've been assuming a linear taper, where there is a one-to-one relationship between the physical position of a screw, knob, or slider and the resistance. This isn't always true, because there also exist potentiometers with logarithmic tapers, where every equal movement on the dial represents a resistance of 10 times the magnitude of the previous position. Logarithmic tapers are sometimes called audio tapers because they're commonly found in audio systems. Additionally, potentiometers with logarithmic tapers are sometimes used as position transducers for things like joysticks. We'll examine logarithms in later lectures. Honestly, there's not that much more to talk about potentiometers other than a general reminder to stay organized when you're using them. It is super easy to dial a potentiometer to the exact resistance you need from A to B and then accidentally hook it up B to C and wonder why nothing is working as you'd expect. Once you figure out which terminals are which, stay organized and use those terminals and those terminals only. Otherwise, you might be stuck holding the wrong end of the stick. Alright, that's about it for today. In conclusion, this lecture took a close look at a 3-terminal variable resistor known as a potentiometer. We examined the construction and behavior of a potentiometer, examined potentiometers in series and parallel relationships, and briefly inspected a couple real-world potentiometers using an ohmmeter. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.